Good morning, everybody. So we've been talking about waves, and we noticed the properties of waves. They have a wavelength, they have a frequency, they can translate through space at a given speed, and we looked at several properties. In particular, we looked at adding them up. So here's a lot of confusing stuff happening, but let's make that a little less confusing. So there's a traveling wave moving through space. It has a frequency and a wavelength. We can change its wavelength. And when we change its wavelength, we change its frequency. If the speed is fixed, wavelength and frequency are inversely proportional. The frequency times the wavelength has to be the speed. So if you increase the frequency, you decrease the wavelength. And we understand, we saw last time, that higher frequencies mean that wave fronts are passing you more frequently in time. And we even saw sound waves. Sound waves, their amplitude is longitudinal. It goes along the length of the axis rather than perpendicular to the axis of travel. So sound waves move through the air like this, and they hit your eardrum and they vibrate it and you hear sound. And the higher frequency, it goes up in frequency. And we saw that happening in real time. We said we could add them together. So here's a wave. Let's bring another wave, a green wave, on top of that. So there's two traveling waves going in the same direction. And if I add them, I can put the sum of wave 1 and wave 2 up there. That's the blue line. And we saw there were some special conditions that we could add them together. If we add them together, let's make their wavelengths the same. So now you can see their wavelengths are the same. And now they're adding constructively. So the sum, the blue one, is the sum of the amplitudes of the red and the green one. But we also found we could add them destructively. It just depends on how the waves are aligned. So notice if I change the alignment, I can get destructive interference, and now the sum wave is smaller. And if I go perfectly destructive interference, I have to make them the same amplitude. I can get rid of the sum wave altogether. So you can completely eliminate the energy and the amplitude in the wave by summing them together. Here's an interesting fact, though. Let's say I reverse the direction of the travel of one of them. So now they're going in opposite directions. And look at that, the sum, when they're going in opposite directions, the sum is a standing wave. You see how the blue one isn't moving now? It's oscillating up and down in space. The red and the green are moving, and they're creating this sum that's a standing wave. So along the standing wave, we can note there's a node right there. The wave function is always 0 right there, even though that's a location in space where there's no amplitude, there's no energy changing. So if you were standing right there, you would be still in space, but somebody standing just a few inches away would be riding up and down on the wave and being tossed around. So you can go to absolutely quiet places in a standing wave, where there is no disturbance or amplitude. That's an interesting effect. We also looked at the other interesting way to add them. We have to get a lot of ways to do that, so we'll go back to our audio. This was our frequency. Let's go full screen on that. And here we found we were adding waves of all different frequencies, so 11 different frequencies and different amplitudes. And we found when we did that, added frequencies and amplitudes, the sum of all the waves together, that canceled out along the wings here and concentrated some energy right in the center. And this happens in nature. Maybe you've seen, if you're scrolling YouTube or scrolling your Instagram feed, once in a while something will come up where there's ships on the ocean and they're going through these gigantic waves. And those waves are usually periodic. So it is just traveling waves, and they can get very large. But there's a phenomenon known as rogue waves, where you just get one gigantic one. So all the other ones are relatively small, like this, and then a gigantic one out of nowhere hits. And this is a very common phenomenon, but you guys understand why that might occur. If you have storms and winds, and you have waves at different amplitudes and different frequencies coming together, there's a chance they're going to add together to just concentrate their energy and give you a gigantic wave in the middle of the ocean. And these things are recorded. The NOAA, the National Oceanic, Atmospheric and Oceanic Organization, whatever that stands for, they have these buoys. So they have things floating out there in the ocean, and they just measure, real time, broadcast how fast they're oscillating, so they can get wave heights. And they'll watch this happen. They'll have just normal storm, and if it's in the Southern Ocean, normal storm can be 15-foot waves. It can be crazy. But once in a while, a wave will come by that's 70 feet high, and the buoy will just go back to normal. But we would expect that because of the way waves add. So let's, we can just continue then with where we were last time. So this is a summary of this. You take, as we've seen, different frequencies, different wavelengths, and add them together. And you add them together, you can form very concentrated wavefronts. You can get all your energy concentrated in one place. And if you wanted to, measure the energy, or the energy included in the amplitude, our measure would be the square of the amplitude, because that's what we want to measure, just a positive number. We do this all the time in science. If you want to get a magnitude out of numbers that will naturally, if you add all the amplitudes together, you get 0, because some of them are plus and some of them are minus. So it doesn't help you to just add amplitude. You have to square the amplitude, and then they're all positive, and you could add them or manipulate them. We did that once before. Maybe it was almost invisible. Anybody think of a time where you would have a bunch of positive and negative numbers, and you'd want to add them up just to have a total positive component? You would square it. And then if you wanted the real magnitude, you would square it, but then you would say, well, I don't really want the square, but it's positive now, so I'll take the square root of it. That's what we did when we decided in gas, the particles are going all over, and they have positive and negative velocities, but we can't add them all up. The net velocity would be 0. So we square them all, and then take the square root back to get the magnitude. We do the root mean squared. Same thing applies here. You go to the square so you can manipulate and add your amplitudes as you go. So this happens for other phenomena. So we've been talking about waves that need a medium to travel in. That means sound waves need air, ocean waves need water, but waves can travel in a vacuum. There's certain kinds of waves that can travel in a vacuum, and you can make that happen by taking charges and alternating their position back and forth. So you can send, that's the easiest way to do it, is take something that has opposite charge fixed and rotate it, or you can think about it as the charge is oscillating up and down. And if you oscillate those charges up and down, what you'll find is the strength, the magnitude of the attraction, as we know, changes. So the energy of attraction between these two, the interaction energy changes. When they're very close, we call that a high interaction energy. When they're far away, that's a low interaction energy. And we could see that happening if you just let that go. So, and you'd also see, if you're just testing how big the force is at any point, you'd also see it change direction, because you'd have first the plus up here and then the minus. And that could go on and on. And this is actually how we create radio waves. We talked about radio last time. You have an oscillator, and that oscillator at the radio station or wherever they're broadcasting gets rocking up and down at a certain frequency, and then waves start to radiate from it. And they will radiate in empty space. So there's something that moves through empty space, and that thing that moves through empty space is this electric field. It's this interaction. So if that wave encounters an electron, it'll start the electron moving, because it's an oscillating electric field. And that's how your radio detects it. Your antenna detects, it's got its metal detectors in there, and when this comes by, the wave starts stuff moving in your antenna at a given frequency, and you detect that. And then, as we talked about last time, you subtract away at the radio station, they add waves together. They add the radio wave, and on top of it, they add the sound waves, sound frequencies. And then you get it in your radio, and your radio has a little device that subtracts away the big radio oscillation, and you just get the sound oscillation. So it can move charges, these things. And it's actually mysterious. You get this thing going, get that oscillator going, plus minus, plus minus, plus minus, it starts to radiate out, and there's nothing there physically that we can detect. In empty space, it does this. It's actually quite similar to how gravity, we can't see gravity, but it warps space, and we're affected by it. This radiation this radiation from these charged oscillators is kind of the same thing, except not in our space, it's in charged space. So that oscillator warps charge space, and charge space has these waves on it. We can't even detect it because we're overall neutral charge. But anything that has a separate charge can detect that. And they go really, really fast. The speed of light. They start traveling through space at the speed of light if you get these oscillators going, and that radiation, that impact, that disturbance of this ether, this electromagnetic space, that disturbance runs out at the speed of light. And really doesn't ever have to stop. Can travel, and we know this. The reason we can see stars is that's what they're doing. They have this radiation. It's in a visible range, so we can detect it with our eyes, and it's warping the electromagnetic space and traveling all the way to us from billions of miles away. So if you just plotted it, here I'm kind of plotting it as they come together and back, just to remind you. So this can generate this wave, and this would be called an electromagnetic wave. The electro part we get, the magnetic part we don't worry about, but wherever you have a moving charge, electric field, you have a magnetic field as well. We won't worry about that part. It's perpendicular. Out here, oscillating magnetic field, but it can cause action at a distance. If you get a charge here, it will start, this wave hits it, and it will start those charges moving up and down somewhere far away. And the interesting thing again, you kind of translate kinetic and potential energy again. You have a situation where you're moving the charges and you go out to low potential energy and then high potential energy, and it's exchange with kinetic energy as the charged particles or the oscillator moves. It travels at the speed of light, 10 to the 8th meters per second. So this is nice because whenever we talk about electromagnetic waves, we fix the speed. We don't have to worry about different traveling speeds for waves. It's all the same. So that locks the frequency and the wavelength together. If you fix C is a constant, then indeed the product of the wavelength and the frequency is a constant, then wavelength goes up, frequency has to go down. So long wavelengths have low frequencies, and short wavelengths have high frequencies. And we see that, and we've seen that intuitively in the waves that we can detect. So on to the next topic. Not too big a change. We're just going to continue to talk about waves. So again, we're in this area where we're talking about light now, the quantum mechanical nature of the universe. In our roadmap of Chem 1, these are the things we're going to try and cover in this section. So we have this alternating electric and magnetic field. We saw this again. This is the same animation of the charges moving up and down, and those charges moving up and down able to affect charges moving somewhere else. It's just very, very, very similar to ocean waves. I'm going to ask Karen if she has a little bit of tape. I want to tape a ball down here. Karen, do you have a little tape, any kind that we can just tape this ball to the cloth? I got Karen some ping pong balls, so we can kind of demonstrate that. We'll need a little help. Let's get some students' help. Do you guys mind coming down, Casey and what's your name? What? Mills. Can you guys come down here? You're just going to help me create a wave on this and look at the effect it has on a ping pong ball. So, Casey, take one end of the cloth. I don't know if Karen heard us. Mills, you can come here, stand where I am. And what these guys can do, pull it tight, this way too. And now, Casey, if you'll just oscillate up and down, if you stay fixed, you can see that we're going to create waves in that matter. And try going at a higher frequency. See if you can get So you can get several waves standing on that. And if you had a tennis ball, let's stop it a minute, a ping pong ball on there, now give me a nice slow wave and kind of try to keep it on there. It'll start being affected by that wave. That's just how an electron would be affected by an electromagnetic wave. Oh my goodness, cool. Can we try to tape it down? I want to watch its motion. I'm just gonna make a loop and try and get it on there. We're just gonna, oh, it's double-sided. Perfect. So we'll give it a little adhesion and see if it stays on there. Now it won't move as much, so give us a little wave, and you can see it's easy to pop it out. Even if it has a little bit of hold on it, the energy of the wave can dislodge the tape. Let's see if we can get more adhesion. Go ahead, give us a wave. So we can't get it in there, but it's easy to dislodge. That's great. Oh, look at all the energy we can give it. That's cool. So you can see that a high amplitude wave would give a lot of energy to the ball. And if you wanted to get it to leave, to really give it a lot of kinetic energy, should you give a high amplitude, a high wavelength, or a high frequency? Yeah, almost any frequency you'd think would work as long as it's a high amplitude as well. So let's try, Casey, give me low amplitude but high frequency. Bounce it around a little bit. So give me now just a high frequency or a high amplitude at any frequency you want. Yeah, easy to launch the ball and get it kinetic energy. That's fantastic, guys. Thank you very much. Little gallery clap for Casey and Mills. Thank you very much. So that happens, that interaction at a distance, we understood that would happen. And we understand because of this electromagnetic, this oscillating electric field that's contained in the waves. There's an entire spectrum of electromagnetic radiation. We've been talking about radio waves, and these radio waves travel through the atmosphere. They're not detectable to us. They're hitting us right now. They're not dangerous. The FCC wouldn't let radio stations broadcast radiation that was dangerous, but it is radiation, called radiation because it's radiating from this source that's causing the ether of charged space to oscillate, and it can be dangerous. We have this gigantic spectrum depending on wavelength. So if you go to the very short wavelengths, you know intuitively, this is common knowledge. These are the different kinds of electromagnetic radiation. The various regions, various bands, you call them, would have names. Radio waves, microwaves, infrared. This tiny little point in the middle is the visible, where our eyes are sensitive. Ultraviolet, and now you recognize ultraviolet, X-rays, gamma rays. These you recognize as the ones that are dangerous. The very short wavelengths, the very high frequency. So in a sense, the higher frequency is somehow more dangerous to us. And indeed, we're worried about frequency, and we're almost worried about it more than amplitude. Amplitude hurts too, but frequency is what makes it dangerous to us. So that's a little odd to start with, what you think. Certainly you don't want high amplitude. We should kind of associate amplitude with brightness, how intense it is. Frequency and wavelength are independent of how bright it is, but it's the frequency that makes these dangerous. So if you had a bright radio wave, it's still not harmful. High intensity, still not harmful, but these are harmful when they're low or high intensity. So there's something in the frequency that is causing the issues. And this spectrum goes on. You have the high frequency, some middle frequencies here, longer wavelength, lower frequency as you go. And I've drawn different amplitudes along the line, all of them traveling at the speed of light. We're taking the intensity now as the amplitude squared. How bright it is related to its amplitude. And the visible spectrum, this tiny bit in the middle, is where our eyes are sensitive to. So, and it is just a tiny bit of electromagnetic radiation. All this radiation is emitted from the sun. Most very bright emitting objects, bright emitters, perfect emitters, emit in the whole spectrum. They might emit, differently at different parts of the spectrum. Maybe you emit high in the microwaves and lower here, or we know the sun emits high intensity in the visible range. We can see it, and infrared, thank goodness, it keeps us warm, and ultraviolet, a little dangerous, but we have an ozone layer that helps us. So all these things are radiating through space. The frequencies, we don't really talk about the frequencies very much. These are wavelengths from 400 to 700 nanometers. And this is one of the things you're going to be familiar with. I'll try to remember, maybe I'll try to put it on the equation sheet. In general, we'll tell you a wavelength, but you should know 400 to 700 nanometers. You should know that's the visible range. We're going to work in the visible range all the time, so that'll help, a lot of practice. And the colors going from red, orange, green, blue, violet, you should basically know the sequence of the colors. The long wavelengths, red, medium wavelengths, yellow and green, the shorter wavelengths, blue. So in a sense, these are high frequency, blue, and lower frequency, red. The only time we really talk about frequencies that you'll recognize are radio waves. Radio stations. Anybody have a favorite radio station? Do you guys even listen to the radio anymore? What is it? Anybody? 80 what? 88.5? What? 96.5, got some fans. Those numbers are the frequency in megahertz. 96.5 megahertz, 101.3 megahertz, 88.5 megahertz. Cycles per second, 1/second. That means when you're listening to the radio, the waves are passing you at 96.5 megahertz, 96.5 million times per second, the waves are passing you. Very high frequency, but it's actually at the low end of the frequency range. The wavelengths, you can calculate it, you know the speed they're traveling, so if you know a frequency, you can translate it into a wave. We should do that as a chem quiz. We'll do that next time. The wavelengths are on the order of hundreds of meters. Meters to hundreds, well, it's there, I guess. You can have radio waves that are hundreds of meters in wavelength. So the wavelength longer than this room. And it's kind of odd to think about. You think about radiation as a tiny thing that you cannot see, but it has this gigantic macroscopic property. It's still, even though the waves are hundreds of meters long, 96 million of them can still pass you in a second. Why? Because they're traveling at the speed of light. So of course 96 million can blow by you in a second. So that reminds me of a funny story. Do you guys have preferences on your radio? Do you still do that? Where you can just, fix one radio and say, so you can just hit the buttons quick. That still happens. When I was in grad school, I was going on a date for a person for the first time, and I was a little nervous, and we got in the car, and my preferences came up, and 88.5 was the top preference, and that's NPR. And so I felt a little, geeky. But it didn't occur to me. She said it. She said, oh, 88.5, that's the top of your favorites list. And it didn't occur to me till she said that one way you can arrange your preferences is by how much you like them. I had arranged mine in order of increasing frequency. So 88.5 was just the lowest frequency. So naturally I'm, oh, you order yours by preference. Oh, well, I order mine spectroscopically. So you recognize some of these things. Microwaves, we're going to talk about that more higher frequency radiation. And then we get into the damaging highest frequency radiations as we move along. So we talked about how things that radiate can be perfect radiators. They can radiate at every frequency in the electromagnetic spectrum. Some dimly, bright in some regions, dim in other regions, but these perfect radiators can emit anywhere. You can make a radiator, you guys, something that radiates. Heat up a piece of metal. We've done it here. They start to glow. First yellow, then orange and red, and then if you get them really hot, they'll glow white hot. And you can tell the temperature by the color. Those perfect radiators, so here's glowing red, emitting red radiation. As I get it hotter, it's going to go into the higher frequencies of wavelength. And then down here when it's white, the reason it turns white for one reason is you start to see a lot of the frequencies. And when all the colors add together, you get whitish light. So the light coming from these light bulbs is white. It contains all of the colors. So when all the colors mix together, it turns white. The reason that happens is things that radiate in the whole spectrum, but not evenly across the whole spectrum. Some of them radiate, so glowing objects that radiate, they have a peak in their radiation in the visible spectrum of the ultraviolet or electromagnetic spectrum. So you see that happening, and you see the various colors. And like I said, you can measure things that are different temperatures have different peaks, different spectra that they radiate at. So you can tell something is hot by its color. It's how we know the sun, temperature of the sun, because we can measure spectroscopically the colors that are coming out. We can measure, we can plot for the sun. We have great detectors. We can plot for the sun this entire spectrum. We can find its peak and correlate it with the temperature of the surface of the sun or any object that's glowing hot. So it's a handy reference. It's how we know, in space, no one can hear you scream. You know that, and we now kind of know intuitively like that. Sound waves need a medium to travel through. So if there's no air or water or something to travel through, sound can't travel in a vacuum. Electromagnetic waves are in their own space. We don't detect it, but they're warping this electromagnetic space. They don't need a medium to travel in. But you probably know that space is very cold. A couple degrees Kelvin, empty space. And one of the reasons we know that is we look at the background radiation coming from space. We look at a place where there is no stars or something. We look where there's no other bright objects, and we just look at the background radiation, the overall radiation, and you plot out the overall radiation coming from space. And its peak is in the microwave region, way down from the visible region, and that corresponds to temperatures of 3 or 4 Kelvin. So that's how we know the temperature of space. Well, here's, okay, so this is just some useful stuff. When you go to the store these days, you can choose the color of your light that you get from your LED lighting, and they rank it by temperature. And now you understand why. Colors correspond to temperatures in Kelvin. So 2700 Kelvin, that's orangey light, and then the light gets bluer and bluer and bluer, higher and higher peak frequencies as you go to higher color temperatures. So next time you're in the hardware store and people are looking at it and they're saying, oh, do I need 3500 Kelvin, 3500 K color temperature? You'll go, well, you know what that is. There's one confusing part about it, though. Notice that they call these colors warm and these colors cool, and that's the opposite of the direction the temperature is going. So that's a little confusing. But that's just where the artists collide with the scientists. To the artists, the oranges are warm and the blues are cool. So artists have their own little scale. We'll let them have their own little scale. And we'll use the temperature scale for our lighting. So here, let's just say that we have an emitter in something glowing, let's say it's glowing white hot, so all the colors are coming out. You can have other things that absorb that color, and they can also, once they've absorbed it, they can emit at various frequencies. And that can happen in a couple ways. You can have, what I've drawn here is an absorption spectrum. We're saying that if all these colors are coming in, something white hot is here, this substance absorbs mostly the greens out of that. It can also happen by emission. That is, you could, something, and we already know, something that's very hot can emit maybe mainly oranges. Something can absorb greens and then emit greens, and we would see them. Or sometimes they absorb high energies, blue, and then something happens and they emit yellows and greens. So they're absorbing this energy from the spectrum. And believe it or not, it can be very precise. It can be kind of these regions of absorption or emission, but it can also be exact specific frequencies in the spectrum. You only absorb at 550 nanometers, just that wavelength you absorb. So there's this odd phenomena where matter can sometimes just pick to absorb or emit just specific frequencies. That's a property of matter. These things turns out are doing the same thing. There's just many of them and they're mished together, so you can't resolve the fact that there's individual things happening. So let me ask you this. What color is an object that has this absorption spectrum? So if the teaching assistants will stand up and talk to the crowd, we'll talk about that one for a minute. Talk through this one. Glass is transparent. Which is its absorption spectrum? So now we're saying, where does glass absorb? Clear glass, the clear glass that's containing these things. Well, it's transparent. What does that mean? That means if I'm on the other side of glass, I see all visible wavelength. It's not absorbing any of them. So we should look for an absorption spectrum that does not touch the visible. If I take any part of the visible, I would see a color involved. And you can make colored glass, but we're going to do transparent glass. If this were the absorption spectrum, it would absorb all the visible light. And what would that look like? Black, no light coming through. If it just touches the visible spectrum and absorbs part of it, then it's going to be some color. If it absorbs none of it, then all the wavelengths pass through and you'll see good color resolution. And you actually may know this, that glass absorbs in the ultraviolet. If you're behind a sheet of glass that's protecting you from ultraviolet radiation, you can't get a suntan inside behind a glass. It's absorbing it all. So that is good to know. Take note of this, please. I put this on a midterm last time, and I said, here's the absorption spectrum of a compound. I have a compound that's sensitive to ultraviolet light, and I'm going to do this reaction in a container. If it's sensitive to ultraviolet light, which of these containers should I use? Well, it depends. Do I want it to get the ultraviolet light or not? In this case, I don't want it to get any ultraviolet light. I want to protect it. So which container should I use? Well, I better use one that absorbs the ultraviolet light. So the midterm question was about ozone or something, and ozone is reacting in the atmosphere, and since the ozone reaction was catalyzed by ultraviolet light. And I think the question was, well, if the ozone reaction is catalyzed by ultraviolet light, would you see the reaction go with this in this container? Well, no, because no ultraviolet light can get into that container. So that's the kind of question we had about this last time. So there it is. In more detail, there's the visible spectrum, the middle of the visible spectrum, and this thing would be reddish because it's absorbing the blues and the greens, and the one that doesn't is there. So let's talk about another just common property of light. Actually, any waves. Waves have this property, and we've seen it. They add and subtract with each other. We can get constructive and destructive interference of waves. And we can see that in a demo. I kind of want to show you the demo first here with just water waves, but it doesn't look like I loaded it up. Oh, poo. Well, it's one of, oh no, golly. Sorry, it's one of these. I don't know which one. Stand by a minute. I'm going to try to figure out which one. The easiest way to do that is to it's probably this one. No, it's not that one. Sorry, poop. Oh well, I'll just see if it is one of these. Sorry, to be a little underprepared here. Can I have that? And can we go over here and look at that? That's not it. Oh, let's just look for, bear with me one second. let's just search here. Oh, come on. I can't. Okay, sorry. Unprepared. It seems like there should be a search function. Oops, there goes the microphone. Poopy. Okay, I can't find it. I'll try to find it next time. It's instructive to do it that way. So waves do this thing, we know, where they can have constructive and destructive interference. So you can make that happen in an interesting way. You can have light come onto a surface and then have two little pinholes in the surface. And if you did that, you might expect, well, if you just have one hole, you have the light go through and you'd get some light intensity on the screen here. And it actually would be bigger than the hole because the light diffracts, it diffuses, the waves diffuse. Even water waves would diffuse out through there. If you had water waves going through a gap, they would diffuse out there. And if you did that, you would say the intensity here is, you can think about it in two ways. Well, it's the amplitude of it's the intensity, it's the brightness at the spot. But you could also think about it as a probability of a spot. It's more probable that the light hits here. You do another slit, you would get that. Same thing, it would have an intensity. The curious thing, it's not that curious. If you do both slits at once, you'd think, oh, well, I'll just get bright and bright. But you don't. You get a interesting reaction. So instead of having the image of this hole and the image of this hole, you get this. You get alternating bright and dark spots. But we already know why that is, don't we? We saw you could add waves together, and if you add waves, there are places where you would get constructive interference, and there are places where you'd get destructive interference. Constructive interference, you'd get brighter light. Destructive interference, you'd get dimmer light. So the fact that this happens proves that light is a wave. And Karen's going to demonstrate that for us right now. She's going to take a laser and she's going to pass it through, shine it on she's already doing it. How do we have to resolve that? Here there's her laser. She's going to put that little slits, her little two slits in front of that, and look at that. She has put in front of her laser beam these little pair of slits, and the little pair of slits makes the laser do that. So this is demonstrating in a way that we understand that light is a wave. So why does it do that? Well, we understand constructive and destructive. Why is it very intense in the middle and then goes out more goes out and gets dimmer. Well, the light still is diffusing. It still is diffracting. So there's a diffraction effect where it's just spreading out. And then there's what you call an interference effect. The waves are interfering with each other, giving you constructive or destructive interference. That we can probably look at in a demo. Here's one here. So here we have light hitting a screen, and we can have, this is a representation of the waves, and this is the representation of a wave if you just had one wave coming through. If I want to show just the diffraction. There we go. If I just had diffraction, if I just had it spreading out, I would see bright and then dim. The interference is a wave coming from this hole, and this is the intensity on the screen. So right here, it would be very intense, and then dim, and then bright, and then dim, and then bright, and then dim. And that's the two waves adding constructively here, destructively here, constructively, destructively. If you overlap on top of that the diffraction, then you see this kind of pattern. The diffraction pattern limits the intensities of the interference pattern. So why does this happen? We can move these various things and look at different wavelengths. So we have 700, that looks red. We can change the wavelength. And as I change the wavelength, you can see I'm going to shorter wavelengths there, and we can get rid of the diffraction and just show the interference. So this is just the waves interfering with each other. And you can see as I change that, the interference, the frequency of the interference pattern is changing. If I change the distance between the slits, I can change the frequency of the interference pattern. And I can see that this is waves. This is a wave behavior. Why exactly does it occur? Well, we can draw on top of this. You got to say this point right here, we have very intense radiation. This point, say here, you have zero intensity. Why is that? Well, we're saying that the waves add constructively and destructively. So if you have a wave coming from this slit and from this slit, and they hit right there, they will add, whatever their intensities are when they hit, they'll add right there, and you'll get constructive or destructive. But look at this. This beam had to travel farther than this beam. So if they were perfectly in phase here, they travel, and this one had to go a shorter distance. So when it got here, it was up. But when the one that went the longer distance got there, it was down. And you got a dim spot. If they travel right there to the center, then they travel the same distance. And when they get there, they're both up. And they give me a bright spot. So it's easy to understand, and we see that that is a property of waves. And that is indeed how we decided that light has wave properties. So that's pretty interesting that we can show the wave properties of light in a very simple experiment. How would it change if I increase lambda? Well, we already looked at the answer, so I will we'll just go through it together. Increasing the wavelength. So if you increase a wavelength here from green to red, does the pattern get more tight, stay about the same, or get less tight? We can talk about that. So we know why it occurs. We have two waves travel the same distance, and they give us this bright spot. Equal path lengths. Here, you've gone up the screen far enough that the waves were in sync here. And if you go up here, you got to another place where they're in sync. This wave is now one full wavelength ahead of this one because they're adding constructively again. They're back to both being straight up. When you're here, you got to a point where the lower one was a full half wavelength behind, and you got the dark spot. So this distance up here is a function of the wavelength. As you go up, if you have shorter wavelengths, they're going to overlap more often as you go up. The path difference doesn't have to be as big to get to the next bright spot. So I said it the other way. Larger space, larger lambda is greater spacing. I said it the other way. Shorter lambda is tighter spacing. So that's what we would expect to see. Does this show it? Oh, this just shows Lonnie doing we're doing live in real time. Okay, so light can be absorbed, it can be emitted, it can also just be scattered, so it can just be made more diffuse when it enters a system, and that happens in the air. Air scatters, any medium will really scatter light, but it scatters it at different frequencies too. So you could say if light is going to be scattered at different frequencies, so this says the blues are highly scattered and the reds are not scattered as much. What does that mean? The color that you would see here. So your light source is here. If you're looking directly behind it, does this scattering change the color of light that you see? Talk about that for a minute, and we'll oops. Go ahead, talk about that one for a minute, and we will take a vote. Excuse me. Oh, I'm sorry, I knocked over your backpack. Should have come from the other. One is perpendicular to it. So you guys, the light, it's if you have the light passing through that media, that white blob there, if you're directly on the other side at position 2, that's the light that passes all the way through. The light, but we're looking at position 1. Is that different than looking from position 2? All right. Okay. Let's see what you're thinking. A lot of us are thinking blue on that one. Why is that? Well, let's go over this again. So I'm standing in one of two places. I could stand here, and the light is going to come right through that medium and hit me. So that's along the path of the light. But I could also be standing here and looking up. Now the light is going there, so it's not coming directly at me anymore. But will I see some light here? And the answer is yes. The light that gets scattered, it's going in here. If it's getting scattered, it's going in all directions. The light that gets scattered less tends to go all the way through. So you can separate the light here. It's not absorption exactly, because if it were absorbed, you wouldn't see it any other place. Same kind of phenomena, though. I'm separating out some light by scattering it away. So the blue wavelengths are highly scattered. So the blue wavelengths are going out like this. The red wavelengths are passing through. Does that remind anyone of any particular phenomena? Why is the sky blue? The sky is blue because you never look right at the sun, do you? That hurts. You look over here, and what do you see? The scattered light. The blues. When can you look directly at the sun, or right where the sun is coming from? At sunset, right? You can look over near the sun, and then what colors do you see? Because it's traveling, you see the unscattered light. What color is the light you see at sunset? Red. And the more particles there are in the air, the redder it looks, because the particles are doing the scattering. So on smoky days, on hazy days, the sunsets are redder than because they're scattered. So I'm glad, you're probably all thinking, oh, I'm so glad I came today. I went to Cal and I said to myself, I'm going to Cal, one thing I want to get out of it is, why is the sky blue? If I take nothing else home for my entire career. All right, now you know. Okay, we can talk about more of that in discussion. All this we'll do in discussion, it looks like. Okay, we'll move on to the next thing here. Where are we? We just did, we want to go here. Okay, we'll continue along to our next thing. We're going to talk about still the tiny nature of the universe, the quantum mechanical nature of the universe, how things happen on a tiny scale. We're talking right now about tiny little wavelengths is the tiny thing we're talking about now. We're talking about 700 nanometer wavelengths. We know that we could have electromagnetic radiation with macroscopic wavelengths, those low energy, low frequency waves. And we've just kind of talked about this. If you have light passing through a medium, it can be absorbed. And now this is absorption, not scattering. We saw it there. We saw light passing through, red light passing through the blue. We saw it pass through. Some of it, though, could have been dimmed by that. So if you could measure the dimming, the overall intensity of the light dropping, you could say, well, let's say this much medium, it dropped by a factor of 2, the intensity. What would happen if you passed that column through another column of the same material and the same length? And I don't think anyone would be surprised if it dropped by another factor of 2. So we're not even we just talked about it. We don't even have to do this one. Yeah, it would drop by another factor of 2. The overall intensity from 2 would have dropped down to a factor of 4 from the original intensity. Now you can continue, you could imagine continuing to do this. One way to think about atomic theory, things are atoms, is you could say, well, I'm going to take a block of carbon, and I'm going to cut it in half. I have half the molecules, cut it in half the atoms, half the atoms, half the atoms, and keep cutting it in half. Eventually, you can't do the experiment anymore. You just have to imagine doing the experiment. But you could imagine cutting and cutting and cutting and cutting and cutting until you were down to the smallest possible particle of carbon. And if you cut it in half again, you wouldn't have carbon anymore. You would be making it into something else. And that jives with atomic theory. We know things are made of atoms, and if we chop it up and chop it up and chop it up, half, 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 we'll eventually get down to 1. What does that mean for light? Here we keep chopping it in half. We continue with light intensity, and so if I have a light over there, and I start putting filters in the path, and each one drops the intensity by a factor of 2. So here's my light source, and I start putting filters in front, and I keep dropping the intensity. It'll get dimmer and dimmer and dimmer and dimmer. And what happens at the very limit of dimness? Does the light stay continuously and then just fade out continuously to 0? It does not. Very interesting. What you see, and actually our eyes are sensitive enough to do this. If you sit in a very, very dark room, and you have very good eyes, young eyes, and you have a light source, and you drop the intensity down continuously till it appears to go out. If you sit there and wait, you'll start to see flashes. Blip, 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 blip. The light will come in bits. So the light appears continuous most of the time. But you can cut it in half and half and half and half and half and half until you get bits of it, discrete particles, for lack of a better word. Particles of light come through, individual packages, flashes of light. So what we were seeing when it was more intense, when it was brighter, apparently is just so many packages, so many blips per second that it appeared continuous. So there's lots of these blips, lots of these particles being carried along the wave, and we never notice that they're there because they're tiny. You have to cut the white light in half many, 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 many times before you can resolve the individual blip. So light has this odd particulate nature. to it as well. It comes in packages. We call the packages photons. Photons of light, the package of light that comes through. And photons have an energy associated with them. And it's directly proportional to the frequency. So the particles of light have a different energy if they have a different frequency. So yellow blips from, 6 or 600-ish nanometer light, they have a lower energy than blips from blue light, because blue has a higher frequency. They're still just a blip, but the individual energy carried in a blue blip is higher, the package is higher than a yellow blip. It depends on their frequency or their wavelength. You can put C over lambda here. You can do the wavelength as well. So shorter wavelength, higher energy. The blue is the shorter wavelength, 400 nanometers. It has higher energy blips. They come at you at the same rate if it's the same intensity light you started with. They come at you at the same rate, but higher energy per blip. So that kind of tells us, we answered a question we had when we first started this. Why is that high frequency light at the end of the electromagnetic spectrum, why is it dangerous when the energy at the other end of the spectrum, same brightness, is not? Because there's parts of us that are sensitive to the individual blips. So each individual blip of a gamma wave is carrying a big punch of energy. And parts of us are susceptible to the individual blips, individual particles of light. So you can have a very bright radio source. So the brightness is how many particles per second, essentially. You have more particles per second, it's brighter. That's more energy because you have more particles, higher amplitude. So a high wavelength is, excuse me, I said wavelength. High amplitude is many particles per second. Brightness is more particles per second. But if the individual particles, if you're sensitive to the individual particles, then they can affect you in different ways. So there are potentially high energy particles in that light, and you can feel a particle, it's going to smack into you hard if you're not sensitive to the particles, or they're just very low energy. You aren't sensitive to them. It can be bright, there can be billions of them per second, but you're not sensitive to the packages that are coming in. So that is why some of those wavelengths are dangerous. The very short wavelengths, the very high frequency wavelengths are dangerous. Okay, we'll pick it up there on Monday. We have exam Tuesday. We are moving the exam time back. We'll post an announcement. You guys that have the lab lecture that goes till 6. Well, let's just take a little quick poll here. We can move it. We're totally flexible. And some of you probably might like to get all the way home who are in that. So we could just move it all the way back to 7, I guess. Is that good? Give everybody a chance to get somewhere quiet and safe. Is 7 too late? Does anybody say no, not 7? Okay, we'll move it back to 7 p.m. We'll send out an announcement to that effect, and you can take it then.